Now we'll see the symmetry properties of Fourier transform. Okay, so this is once again going to be exactly the same as what we saw in the Fourier series, because this is after all just a set of phasors. Earlier we had discrete phases, now we are going to have continuous set of phasors. So the symmetry property does not really change, and we'll see why that does not change. So all we need is the same relationship that we had earlier, that x of t is equal to 1 by 2 pi minus to infinity x of j omega e power j omega t d omega, and x of j omega is just the inner product that's all. So if the time domain signal is even, what about the frequency domain signal? So if the time domain signal was even, then what does it mean? Then it means that x of minus t is equal to x of t. So how do you show this? So it's quite simple. All we have to do is take x of minus j omega. What is x of minus j omega? It is minus infinity to infinity x of t e power minus j of minus omega t dt. This is x of minus j omega. Okay. So now all we have to do is just once again do the substitution operation. Just say that v is equal to minus t. Okay. So if you just substitute that v is equal to minus t here, so we get x of minus v, and this minus can be shifted to v, which means this is omega v, and now dv is equal to minus dt, and we have dv here. So there is a minus. This limits also change, because when t is minus infinity, v is infinity, and that minus gets cancelled out with this minus. So we have this expression finally. But because x is even, now x of minus v is also x of v. So now we get exactly the same expression as the Fourier transform, which means this is equal to x of j omega. Now this gives us the relationship that the spectrum is an even spectrum. But the same thing, if we do the same operation, if we assume that x is odd signal, then we have the relationship that x of t is minus of x of minus t, and here x of t is x of minus t. So if we substitute this here, what do we get? Then we get that this is minus of x of v. In that case, there is a minus that comes outside, so there is a minus here, which makes the spectrum also to be odd. So if the time domain signal is even, then the spectrum is also even. If the time domain signal is odd, then the spectrum is also odd. Okay, so keep that in mind. Now, what if the time domain signal is conjugate symmetric? So if the time domain signal is conjugate symmetric, what does it mean? So it means that x of t is equal to x star of minus t. So that is the meaning of conjugate symmetry. Now what is the consequence of having a conjugate symmetric time domain signal? Now let us see that. So let us say that x of j omega is equal to, so we know the expansion here, so just simply replace that x of t here with x star of minus t. Okay. If you replace this with x star of minus t, what can we do? The first thing that we can do is take this conjugate outside. So if you take this conjugate outside, then we get x of minus t times e power j omega t dt, the whole conjugate. Okay, because the conjugate of e power j omega t is e power minus j omega t. Now do the same substitution again. Let us say v is equal to minus t. If we say v is equal to minus t, then we have this whole thing to be equal to minus infinity to infinity x of v e power minus j omega v dv. There is a sign change here and the limits also change, so the sign changes get cancelled out. So finally this is what we have. This is exactly equal to the Fourier transform of the original signal, which gives us that the conjugate of the spectrum is equal to the spectrum itself, which can happen only when the spectrum is a real signal, right? Only for a real signal, its conjugate is equal to itself. So which automatically means that the spectrum is now real. Going by the same logic, if time domain signal is conjugate asymmetric, okay, then what do we have here? So we have a negative component. So this becomes minus. So there is a minus in front, okay, and that comes outside and that comes outside here. So now we have something where the signal is equal to the negative of its conjugate. That is possible only if the signal is purely imaginary. So whenever the signal is in time domain conjugate symmetric, then the spectrum is completely real, and whenever in time domain it is a conjugate asymmetric signal, then the spectrum is completely imaginary. So keep this in mind. So these are complex signals, right? So whenever you have a complex conjugate asymmetric signal, even though the time domain signal is complex, the spectrum can be completely real, or if it in the time domain is completely conjugate asymmetric complex, then the frequency domain is purely imaginary. This is once again very similar to what we saw in the Fourier series case. Now what if we have a real time domain signal, which is what we will encounter often, right? So if we have a real time domain signal, what does it mean? Then it means that x of t is equal to x star of t. Okay, so we can do the same thing. So this is our actual time domain representation of Fourier transform. Now we will just simply replace this x of t with x star of t. Okay, why is that? That is because that's what is given to us. X of t is real, so both are equal. So we will do the same thing. We will take the conjugation outside. So if we take the conjugation outside, we have x of t e power j omega t dt. The conjugation is outside here. Now what is this? Now we can rewrite this as integral x of t e power minus j of minus omega t dt, the whole conjugate. So what is present here? So what we have here inside this integral is basically nothing but x of minus j omega, and outside there is a conjugate. So now we have exactly this relationship, but for the spectrum. So the spectrum now becomes conjugate symmetric whenever the time domain signal is real. And similarly for the case of imaginary, whenever we have an imaginary signal, which basically means x of t is equal to minus of x star of t. Okay, so this is the condition for a signal to be purely imaginary. So if there is something that is purely imaginary, then we get a minus here outside, which means there is a minus here, which makes a minus here, which is the condition for conjugate asymmetry. So something that is conjugate asymmetric in the frequency domain results in something that is purely imaginary in the time domain, and vice versa. So now this gives us a very nice decomposition of any signal. Okay, so this decomposition is quite interesting. Now you can take any signal that is given to you, x of t. It can be an arbitrary signal. So if it is a complex signal, you can always split that into a real part plus a purely imaginary part, and otherwise you can just split it into a conjugate symmetric part and a conjugate asymmetric part. We know how to do this. So this is true for any arbitrary signal, right? Any arbitrary that is signal that is given to you, you can split it always into a real part plus an imaginary part, or a conjugate symmetric part plus a conjugate asymmetric part. Now let us say we split like that, and if we try to find out their spectrums individually, how are they related? They are related in a very interesting fashion. Now if I try to find out the spectrum of the real part of the signal x of t, what is that we get? So how do I get the real part of x of t? The real part of x of t is after all nothing but x of t plus x star of t by 2. This gives the real part of the signal, correct? So this is essentially what, if I take the Fourier transform of this signal, x of t gives me x of j omega, okay. And what is the Fourier transform of the conjugate of a signal? We saw this earlier, right? So the Fourier transform of the conjugate of a signal is nothing but the conjugate with the frequency is reversed. So the Fourier transform of the real part gives us something which is nothing but the conjugate symmetric part of the spectrum. So if I given the spectrum x of t, how will I find the conjugate symmetric part? Exactly using this formula, right? So if we compute the Fourier transform of the real part of the time domain signal, then what we get is nothing but the conjugate symmetric part of the spectrum of the original time domain signal. By the same reasoning, we can also tell what happens in the other cases. So if I want to find the imaginary part, then what do we have here? The imaginary part is nothing but the negative. So what is the corresponding change here? There is a minus here, which gives us the conjugate asymmetric part, right? So this exactly corresponds to the conjugate asymmetric part now. So the real part of the time domain signal gives us the conjugate symmetric part of the spectrum, and the imaginary part of the time domain signal gives the conjugate asymmetric part of the spectrum. Now what if we don't split that into real part and imaginary part, but directly split that into the conjugate symmetric and asymmetric part, okay? In other words, we'll do the other side operation. So how do we get the conjugate symmetric part of x of t? So we take x of t, add that with x star of minus t, and then take the average. Now if we apply Fourier transform, the Fourier transform of x of t is x of j omega. And what is the Fourier transform of x star of minus t? The Fourier transform of x star of t is x star of minus j omega. So this is for x star of t. Now if you are just reversing the time, then there is a reversal in frequency, which means this is the new spectrum. So this is the spectrum that corresponds to x star of minus t. Once again, all we did is just use the properties we just studied. We just studied what happens to this spectrum whenever there is a conjugation operation in time domain, whenever there is a time reversal and all, right. Those two properties are all that we are using here. So clearly this is nothing but the real part of x of j omega. And hence the Fourier transform of the conjugate symmetric part produces the real part of the spectrum. Now for the conjugate asymmetric part, now let us say that we are trying to find the conjugate asymmetric part of x, that is given by this expression, just a change in sign here. So x of t minus x star of minus t, that gives the conjugate asymmetric part. Now let's take the Fourier transform. The first term gives x of j omega as such. Now the second term, here there is a minus, that's the only difference. It's all the same otherwise. So we have a complex number subtracted with its conjugate. So we'll get the purely imaginary part of this number. So this is nothing but the imaginary part of the spectrum of the original signal. So that's exactly what we have. So this is a very nice relationship that exists between the symmetric parts and the real and imaginary parts of the time domain signal and the spectrum of that signal. So this is very, very important, and this is something which once again we'll use very often in a lot of our analysis where we'll say that if we have a complex signal inside a circuit, like, so often we model signals in a circuit as complex signals because of different phase shifts introduced by capacitors and inductors. So when we have a complex signal, then we know that the spectrum has to be containing both the conjugate symmetric part and the conjugate asymmetric part, and we can relate what happens in the spectrum due to the real part of the signal and due to the imaginary part of the signal, and the other way around. So if I have the spectrum, I can clearly say that the real part of the spectrum is contributed due to this component of the time domain signal, and the imaginary part is contributed due to this part of the signal. So lot more insights can be obtained in real life when we know these properties, and this becomes very, very handy. So this is something that you have to keep in mind when we talk about Fourier transforms.